June 26, 2023. Welcome to another exciting episode of Descriptive Differential Dynamics, where all things about the descriptive differential dynamics fall under one roof, supported by one foundations. It's the same thing. I was reading this book that I've been kind of enjoying. It's from a guy named Daniel Cohen, and it's called Equations from God, and that's pretty ambitious. But what it describes is the revival of Platonism, the ideals of Platonism, in the 1800s, which is the 19th century. And in the 1800s, the 19th century, he talks about Coleridge, and he talks about Samuel Taylor Coleridge, a poet, and he talks about Augustus de Morgan. And Augustus de Morgan is very famous for the rules of logic writ large and writ down. That de Morgan's rules, when they show up in terms of the propositional calculus, really help to inform and enforce what are the limits and the bounds of inductive inference and causality and connectives. So that's logic, classical, propositional. Vis-a-vis the predicate logic, which is in terms of functions which indicate the Boolean. So Boole and De Morgan are very closely of a time and a place, about the 1850s. And so this notion of this book is, it really goes about the history and about the revival of Platonism after empiricism, and kind of the rejection of Hume and Locke and the empirical, and what arrives at that the not Neoplatonist so much, but just plain Platonist, and then the stronger Platonism gets into, he goes a lot into about how in the sense it needed a shelter, it needed a place, just mathematics of a sort, and what people see as the truth and the search for truth. So that's kind of why it's framed in terms of the deity, because it's associated with the same thing. And that there is one, he has one, a true mathematics. And so that's kind of interesting, and it really brings a lot to bear to help enforce what was the time and place, the the success of the empirical formulas, which these days we know is much more of a fundamental physics, and many more of the convergent phenomena earlier explained by empirical formulae are explained by more fundamental and elementary logical formulae in the fundamental. And at the same time, it was people were rejecting the religions and church because of that, or they were having a hard time making apologetics for it, and finding like-minded people about it or something like that. So it was a time, from the 1850s to the 1870s or so, where then that it became that in England, because the subtitle of the book is like Platonism in the Victorian era or something like that, in terms of the mores and the morals and the vicissitudes of the time. It's pretty interesting if you're a student of history of the development of the revolving cycles of the history and then thoughts about the Platonism as stronger Platonism and strong mathematical Platonism, that it can help to arrive at something that's pretty much useful as a philosophical sort of reckoning that makes it so then to help illustrate that for all sorts of these people, especially about Coleridge and the poets, that poets see truth in mathematics too. And so, and as far as it goes, metaphor, and it fails in the logical, only if only in the extremists, because the words run out, but at the same time, it can reflect on the same thing as any other expression in mathematics or logic. That then, in terms of formality and so on, that it's a matter of when that suffices, and how and whether in what context that suffices to establish the bulwark of the existence of the foundations resulting truth. That truth is this sort of indisputable. So before, when I talk about a Comenius language, where Comenius was kind of the first publican of public school, who was one of the first people to advocate for general education of all people, vis-a-vis the learned class or what it may have been at that time, and Coleridge. So now it's kind of a Comenius and Coleridge language to help describe some of what goes into this theory of truth, and then that it starts with simply that only truisms or well-formed formula that via the lack of paradox, one of them is just a prototype of a fallacy or a lie, that the sentence is not true. And then with regards to the negatory and affirmatory and later the logical, and all this being purely logical, how it arrives at then that those are objects, the elements, the primeval of the primary, and what result the central and the extremes. So that's logic in its universe in a nutshell, where in a nutshell basically reflects that inside the nutshell is a full meal. All right, so we're talking about the geometric and arithmetic mean, and hopefully we'll be able to figure out something about it today. So what we got up to is using the methods of inequalities to establish in the sequences or chains, but sequences of extensionality for equals. Then there's these ascending or descending sequences or chains for the inequalities, and there was discussion about how when it's equals that you can always just replace equals. And so in a system of equation, it's a little underloaded, because a system of equations also means systems of equations in different variables, different equations solving for different things, where you then solve for a system of equations of n variables and n equations or something like that, give or take. But here it also refers to derivations and basically succeeding derivations down the page that are equations as of defined and justified by the initial equation and the transformation on that, so that they're related in that sense, that they're derivable from each other, and they're in a sense equi-interpretable. So then the idea of these forms, where they have the extensionality and results out for these systems of equations, then the systems of inequalities are quite as well simple, except that they just simply represent an ordering, and they have basically the strong ordering property of the existence as of an arithmetization or an algebraization or a geometrization, that like any other one of those with an ordering on it, its elements would fulfill same. And then that with regards to how that's used to describe how to make some of the methods to determine the upper and lower bounds of things, is then for that making for cases of induction to establish something that's so inequalities, and then in terms of either side, when that was in inequalities, to make it up, and so that then where the summation or product does not have the index of summation or product as part of expression, it basically is multiplication by a constant, the count of the indices. And then where otherwise the value in the expression actually varies according to the index of summation or index of production, then that gets into where it doesn't, and that gets into what would be a good and useful way to make frameworks for various expressions, like 1 over 2 to the I, that being 2 to the negative I, the sum of which for I from 1 to infinity is 1. And these kinds of things. Then with regards to useful forms of those for pi and e, those being the other constants of a sort, with those kind of constants, everything else is built off those. Ratios and products and powers and exponents and roots and logarithms and their inverses, expressions down off those. And so there's, when you talk about a sum or product, it is usually of a sort of, it's always adding together or multiplying things together. Is there something like the refinement of continually subtracting something? What does that look like over time, besides is how it looks like when it's all of them done? You just put a negative sign in the expression in that sense. Ditto, just 1 over to make it the inverse. But I bet it's also possible to look at those in various ways about how the diagram would result from the system of equations and system of inequalities, and those forming across one way and down one way, and then in columns, each of them, that you might imagine how those can then also be built in a box with a top and a bottom that then adds from the top and subtracts from the bottom, or vice versa. That is usual other side of something that's inductive, and for induction and inductive inference, and it's here it's framed generally in the sense of meeting in the middle, and then variously where it's the middle of nowhere. All right. So that's about what we've reached in terms of elementary approaches, forms, and usual useful approaches in finding derivations and theorems for objects in these expressions that result more theorems that result more theorems that result the theorem you want. Or a goal. The goal is a goal. Yes. From this result, we obtain our final estimate. ... We shall continue to use summation notation wherever it is convenient. All right. And so then there was discussion of x squared minus y squared, and some about the shape of that, and then geometrically, when the square of integers is like so, to figure out a continuous function between when for a given size of a square and that plus one and that minus one, when a box is that much bigger and it yet shrinks down only like 37 36 or 36 37ths vis-a-vis 36 35ths, that as a product, that's just 37 35ths, or x squared plus 1 over x squared minus 1. And the idea is to figure out what kind of mean is that, or as a formula, as a function of numbers. And then also to make that for a function to find on real numbers. And well, what's the point of that? Well, it essentially reflects some bounds that would help reflect for something like the triangle inequality, to make something for like a squareness, or a granular square mean, is what I've been calling it so far. I just made that up, but as long as the words are correct, and then you can make derivations, is true. And it might be useful also. So here we go, the theorem of the arithmetic and geometric means. Consider the conjecture of all rectangles of area 1, the square has the smallest perimeter. It is clear that a long skinny rectangle of unit area has a much greater perimeter than a fat one having the same area, and the natural guess is that the square has the least perimeter as it is the fattest rectangle. That all regular polygons have the least perimeter for their area is because the circle has less. The circle is the smallest shape for the most area. So it's the roundest. Yeah. We now have a credible conjecture, but how can we prove it? One possibility is to restate it in algebraic form and to attempt to prove the algebraic statement. Let us do this. Suppose we are given a rectangle, we choose our unit of measure so that its area is 1 square unit. If its length is x, then its width must be 1 over x, and its perimeter 2 times the quantity x plus 1 over x. So here it's kind of this reminds me of a couple things. One, it reminds me of the identity dimension in x and 1 over x, the hyperbola. And so I'd be looking to attach these things to the little diagram of the identity dimension that's been being built up over the past 30 hours or 40 hours since I started talking about it. Then there's the other idea is about e to the x plus e to the minus x. And what is that? It's kind of like cosine and sine, or they're functions that together make complements, and so that a power series up in one or down in the other, as according to the positive or negative exponents, ends up making the either way, it's going to kind of fill in the corners. And so here what the author has written about is x plus 1 over x. And about in the case when that's 1, that it's just, you know, x 1 plus 1 over 1 is just 2. But here and here about how it's more square or circular in the middle, and then what happens when it's elongated or flattened. The perimeter of the square with area 1 is 4. So, thus we may restate our conjecture in the form 2 times quantity x plus 1 over x is greater than or equal to 4 if x is greater than 0. With equality only if x equals 1 or x plus 1 over x, that quantity is greater than or equal to 2. With equality only if x equals 1. In terms of greater than and equal and greater than and equals. So is there a way to look at it out in infinity that makes it so that it's any different? Well, in a sense, but it's about the halving spaces and the doubling spaces. That if you divide all the if you divide the line segment between 0 and 1 and these line rails, then they're the points in a line. Compared to the field rails, are points on a line. That the field rail is basically the limits above and below define the two sides of the points on a line. Whereas in the line rails, it's just between 0 and 1, and it's kind of only half stood up on the points in a line. It's one-sided. So the idea is then if this is the whole idea of the Vitali's measure and doubling space, kind of like instead of Banach-Tarski just having like their doubling space in 3 dimensions, that first it's Vitali's and Hausdorff's, but it's Vitali's doubling space in 1 dimension, and that the unit line segment, when you split it up into infinitely many bits, doubles. It's a doubling space. And that's similarly then as so with stuff like the natural unit equivalency function or sweep. Its integral is twice what you'd expect. And so here it's very contrived, though, to think about a quadrilateral and to squish it, to flatten it to infinity, but it still preserves the paralleliness. It still preserves the property of being a parallelogon, and it still preserves the property that its angles are perpendicular or orthogonal. They're right angles, and then as it's flattened, that the opposite sides shrink to 0, while the other opposite sides extend to infinity. Then if that was flattened all the way to the line, kind of like Dirac's unit impulse function, which is a half infinite spike at the origin, and the area under E equals 1. Here the idea is that, well, if the Dirac delta is a unit, is an infinitesimal or point width spike at the origin whose area equals 1, this is Dirac's delta function. It's not a real function. It's modeled by standard functions that approximate it in the continuum limit or in the limit. And we used to say it's a limit of functions. These days, sometimes they'll say it's a limit of distributions or a distribution, but it's just a limit of functions. And it's very widely used with applications in differential analysis. Dirac's delta function, the unit impulse function, that it is, say, half of one of these boxes, and it has area 1. So what about this infinitely stretched or infinitely flattened square? Is its area, could its area be 2, like otherwise this one is? because then as to whether that is the other case for equals. Otherwise, it's always strictly greater than. And then it's an example of one of these things that happens at infinity that belies all the finite inputs, and it would be antinomous, but instead we have deductive analysis like this in the whole space of things. So we arrive at then this beyond the inductive impasse, there's a meeting in the middle of nowhere. And then with regards to it not being a real function, or not a standard function, it still has real character because of the development, for example, just as so, that I've just described, that can be simple. And it's about the revitalization of measure theory. So back to the origin and the near surrounds of it. The next problem is to find a way of reducing the statement to one whose truth we already know. The thing to do is multiply both sides of the inequality by x. Then it becomes x squared plus 1 is greater than 2x, greater than or equals to 2x, and then he sets it up as a polynomial, and to find its root, x squared plus x minus 2x plus 1 is greater than or equal to 0, which is x minus 1 squared. The combination x minus 1 squared appears to the eye now, and we rewrite the last inequality as x minus 1 squared greater than or equal to 0 if x greater than 0. One thing about the facility with dealing with inequalities, which are just like equalities, except they have one or the other greater than or less than, is that when you multiply both sides by a negative number, it changes direction. And would we say that changes the sign of the equality? You could in a lot of cases. It's one or the other, and so it changes the direction of the inequality, and you could though say if you said it changes the sign, because basically it's about that multiplying by -1 changes the sign of something, it would be probably understood. The statement is obvious because the square of a real number is never negative. Several proofs of this theorem, each different from the one given here, may be found in Chapter 4 of E. Beckenbach's and Art Bellman's An Introduction to Inequalities in this series, the Mathematical Association of America New Mathematical Library. If we can reverse our reasoning, we shall have discovered a proof of 3. Let us try to do so. So it's been shown that x minus 1 squared is greater than or equal to 0, so that shows that x minus 1 is greater than or equal to 0, because you can take the root of both sides, as a matter of fact. By theorem 2, the fact that x minus 1 squared greater than or equal to 0 is equivalent to the inequality x squared plus 1 greater than or equal to 2x. So what he does is he employs this theorem that we talked about last time about, and I'm not sure what the name for this is yet, about what was used to establish this first kind of foray in these roots about this n squared plus minus 1 about 1 over root n with regards to 2 times the quantity root n plus 1 minus root n, and 2 times this quantity of root n minus root n plus minus 1, excuse me, minus 1. So in that sense, he appeals to said previous theorem to establish the case and so forward. And he says that it's equivalent to the inequality x squared plus 1 greater than or equal to 2x. If x greater than 0, we may apply theorem 3 with c equals 1 over x to this inequality and find that x plus 1x is greater than or equal to 2 if x is greater than 0. And then he says clearly equality holds if and only if x equals 1. And that's defining where it's equal, that's the minimum. And otherwise that it would be greater. So he's looking for a minimum, and so this is his way to go about establishing that algebraically, according to that the sides of a rectangle, this parallelogon or parallelepiped with the right angles, that it have the expressions of their sides in terms of x over 2 and 1 over 2x, or this 2 over x, and that in terms of the perimeter of a unit area square, and that also being the formula for the whether that's the least is a thing that he showed that the relation to the algebraic terms x plus 1 over x is greater than or equal to 2, and that it's only so in this case. So there's no other shape of a parallelogon like so, a right parallelogon or a rectangle. All right. Our main objective in this chapter is to generalize the simple theorem embodied in 3, which is that x plus 1 over x is greater than or equal to 2 if x is greater than 0. And so I'm kind of thinking about this in a couple different things, because it's the sum of an element and its multiplicative inverse. So for two kinds of operations in arithmetic, it's the complement of an addition formula and what would be their complements. So otherwise, if it was just a number minus the number, it's minus its inverse in the same operation, it's the identity. Similarly, if it was the number times its inverse, it would be the identity. And in the operation, it has its identity, and the operation has its inverses. But across these operations, it has these varia. And so it'd be simpler with roots and logs, and then it's similar with these other scale orders that have been talked about, the incremental and addition, the multiplication and powers, and the exponents and tetration. It's about what regions they sweep in these extremes in the quadrants, and what points at infinity they share. The linear ones share a point at infinity. The exponential ones share a point at infinity, in terms of that being a very wide point, but they have the same properties asymptotically. They do in various laws of large numbers. Here, that the idea about this particular expression that the author has chosen, Kazarinoff, he says, we're going to use 1 plus 1 over x is greater than or equal to 2 a lot. Because it's about addition formula of 1 and 1, which would be just the term normalized to unity plus itself. And particularly where it's smallest when this happens to be so, particularly about the case that it's about this same kind of concept as halving and squaring the box that's been talked about since the path integral talks. And what gets into it is this the fact that the unity, as in the arithmetic of addition, is as well the smallest non-zero element, besides the fact that it's the multiplicative identity. That zero, and then that 0 is both the multiplicative identity, the multiplicative annihilator, and the additive identity. And so when there's this relating expression here of terms of value plus value operation 1 inverse, which equals 2 operations identity, is a lot about the quadratic, and that 2 squared equals 4, and 2 plus 2 equals 4, and these sorts of things that are very well employed throughout the use of the quadrature and numerical methods generally, as was discussed. So it's, yes, 2 plus 2 equals 4 is not just one of the most well-known facts, it's also profound. To generalize the simple theorem embodied in that theorem. The result, x plus 1 over x is greater than or equal to 2 for x greater than 0. It says that the sum of two positive numbers whose product is 1 is a minimum when they are equal. What can we say if more than two numbers are involved? A direct generalization of our inequality 3 is theorem 6. The sum of n positive integers whose product is equal to 1 positive numbers, the sum of n positive numbers whose product is equal to 1 is always greater than or equal to n. Equality holds if and only if all the numbers are equal to 1. So this is it's established that if a number is let between 0 and 1, multiplying it infinitely many times equals 0, goes to 0. And multiplying it infinitely many times, if it's greater than 1, goes to infinity. Sorry. And if it's 1, it's 1. So there's the three kinds of points at infinity where they live, 0, 1, and infinity. And so here then it's discussed that for any pair of numbers like 2 times 1/2 times 3 times 1/3 times 4 times 1/4, that it's clear when it's a finite collection what its product is, that will always be greater than 2 times 4. 2 times the index, 2 times how many pairs, how many is in a pair times how many pairs. That is if a sub I is greater than 0, I equals 1 to n, and if a1 dot a2 dot 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 an minus 1 dot an equals 1, then the sum from 1 equal to n of the a sub I is greater than or equal to n. With equality holding if and only if a sub I equals 1 for each I. What if there's 0 and infinity? Then it's only equal if it's in, it's obviously not equal. Here the idea is to figure out given one of the numbers in relation to I is a various ratio, what is a higher lower bound than n? If one of the numbers in this sequence is multiplied together is like so, then the lower bound goes up. But at the same time, all the other numbers would have a smaller contribution. Then there's also thinking to figure out, well, what's necessary for that to get to n squared? What's necessary for that to get to n cubed? And then powers, and then these other various realms and regions. And I don't have much facility yet to describe how to make that fungible. I'm beginning to get a sense of it. I'm trying to figure out how to make it fungible. Then that such matters after it's made tractable and worked out and boiled down to identities and formulas and expressions and theorems, then that it would be a thing. So here this is given as a theorem, and its proof is postponed till some pages later. A geometric interpretation of this theorem is, if the volume of an n-dimensional box, a rectangular parallelepiped, is 1, the sum of the lengths of its sides is least when it is an n-dimensional cube. You are most familiar with the cases n equals 2 and n equals 3 of this theorem. Of course, one cannot easily visualize a space with dimension greater than 3. Yet today, mathematicians frequently consider problems in spaces of dimensions greater than 3 and even spaces of infinite dimension. Sometimes they talk about HALMOS, finite and infinite dimensional vector spaces. Number theory and compactification of the integers and a point at infinity. Those are infinite, but then in the finite, then there's all kinds of things that go on, like with Eli Cartan, reflections, rotations, and the complex numbers and this and that. But also geometry and regular geometry, and then packings. N.J. Sloan's and John Horton Conway's book on sphere packings is about 1,200 pages thick, and has got as much or more detail about geometric identities as I've ever seen gathered in one place before. It's a greater book. The case n equals 2 of theorem 6 may be stated in another form. If b1 and b2 are positive, then use a1 equals b1 over b2 and a2 equals b2 over b1. And so he writes those terms out as b1 over b2 plus b2 over b1 instead of 1 over x and x greater than or equal to 2, with equality only if b1 equals b2. And he says, given n positive numbers b1 through bn, what is the restatement of theorem 6 in a form like that of inequality 4? So that theorem 6 was this the sum, and then here it would be just that it's like so. And here he defines the arithmetic mean. The arithmetic mean, A, of n numbers, a sub 1 through a sub n, is the sum of the ai's 1 through n over n. Also, you can for example, it's a product that only kind of carries, it's memoryless. And so when computing it, so for a given population of samples, you can compute a sample average, a sample mean. The sample average is the average value of the samples you collect. And so the weight of that is how many samples is in it. So if you pick another same size sample set, and then also compute its sample mean, then you can compute that as in terms of the memory or the weight of it, the same. But otherwise, if you have like 1,000,000 samples and you get a new one, it's not quite clear that whether it's the millionth or the millionth and first, what you can divide it by to figure its contribution to the difference from the existing average or its contribution to the weight of the average. So then you get into talk like moving averages and these kinds of things that end up becoming quantities, and then whether they are summary statistics, whether in terms of memory and the memoryless that they can be maintained, and then whether they get skewed or off weight, off balanced. Here though, it's just defined for a set of numbers. They have an arithmetic mean. So let's see if we can get to what it says geometric mean is. The arithmetic mean of a collection of numbers is often called their average. If the truth of either one of two theorems applies to the truth of another, then we say that the two theorems are equivalent. The following proposition is equivalent to theorem 6, but is more convenient to prove. We shall prove it first, and then use it to prove theorem 6. Product of n positive numbers, theorem 7. The product of n positive numbers with a given sum is greatest when they are all equal. One way to consider this is assume it's not, and then there would be a pair of them that that would make for after their average that it would sum out or something like that. The idea is that the algebra and the geometry it makes it possible to consider what would be rows, pillars, columns, and files out on the n-dimensional cube or tesseract, say, in terms of for as many of the variables there are, that there's one of those that's its own square. And so it's just before I get further into this, because I'd wonder if it would use the same methodology in reference to this proof that was built up about this n squared plus 1, n squared minus 1 bit in the first section, where it holds, as the author will so proceed with it here. Of all, geometrically, this theorem says, of all n-dimensional boxes which have the sum of the lengths of their edges the same, the n-dimensional cube has the greatest volume. Still another equivalent geometric statement of the theorem is, if a straight line segment is subdivided into a given finite number of parts, the product of their lengths is a maximum when they are equal. There's a difference when they're greater than 1 or less than 1 on these products, and so it's kind of with regards to whether the smallest of those pieces is called at minimum length 1 or not. About the usual that 0.5 times 0.5 is 0.25, whereas the sum of 0.25 and 0.25 is 0.5, whereas the sum and powers of the twos is 4. The sum of the negatives and the powers in 1/2 or like so. As we promised above, we shall first prove theorem 7, and then we shall use the theorem to prove theorem 6. Proof theorem 7, which is given below, is based on the idea that if the n given numbers are not all equal to their average, then 2 by 2 we can decrease those above the average and increase those below until all the numbers are all equal, all the while increasing their product. It would be difficult to work with a number all at once. It's much better to approach them 2 at a time. So this is the general notion of the pairwise, that the pairwise is treating elements of a sequence or array as a pair at a time. And that this is the usual notion of the embarrassingly parallel and making for linear speedup when it's possible to operate on data pairwise, that their result is also a datum, and then it can be operated on a piece until they're added up by any number of parallel adders together. The result is sum or product. And otherwise the idea is to be organized otherwise, like, well, we kind of have something that just kind of starts sweeping off the layers and then finds the contributions as that gets deeper and deeper, whether or not it behaves just like sweeping or shoveling snow, or otherwise kind of like so, whether that's massive wide compared to like linear speed up, embarrassed parallel, that it's essentially vector instead of, and superscalar instead of pairwise. And then in the higher levels of theory, that's when we talked about the univalent, and whether you can take a union. It was like, I have an infinite set, I'm going to take the infinite union, compared to otherwise it's like it's got to be all the pairwise bits all bubbling up until they form one giant bubble. These are not necessary consistent concerns. In fact, they're not, and they're separated by an inductive impasse either way. And so this kind of notion of ultimately the pairwise or ultimately the univalent, 2 different things. a very strong aspect of the arithmetic is that the operations are closed on the elements, and so the operands as applied by the operators result the same kind or type of operands, and the same operators apply. So they're always pairwise summable together. Since the proof is slightly complicated at first reading, an example which illustrates each step in the proof is presented in parallel with it. Proof of Theorem 7. If all the n numbers a originally given are equal to big A, then equality holds in phi as stated. If one of the given positive numbers is unequal to a, then there is at least one larger than a and at least one smaller than a. And then on the left-hand side, he says, pick one smaller and one larger, call them a sub 1 and a sub 2, and write a sub 1 equals big A minus h, and a sub 2 equals big A plus k. Of course, h and k are positive. We should now change a sub 1 and a sub 2 so as to increase the product of the n numbers a while keeping their sum fixed at n big A. Let a prime sub 1 equals big A, and let a prime sub 2 equals big A plus k minus h. Then a prime sub 1 plus a prime sub 2 equals 2 big A plus k minus h, just sum those together, equals a sub 1 equals a sub 2. Hence, a prime sub 1 plus a prime sub 2 plus a 3 plus dot 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 plus a n equals the sigma of from 1 to n is the a sub I equals n a. And then he says clearly a prime 1 and a prime 2 are positive. We now have a second collection of n positive numbers whose sum is the same of the original n numbers. And then on the right-hand side, it says, for example, suppose n equals 4, and suppose the given positive numbers are 2, 3, 5, and 6. Then a equals 4, and none of the given numbers is equal to a. We may choose a1 equals 3 and a2 equals 6. Then a1 equals 4 minus 1, and a2 equals 4 plus 2, so that h equals 1 and k equals 2. And so he has the narrative kind of accompanying the symbolic definition with the examples plugged in. We shall now change 3 and 6 so as to increase the product of the four given numbers while keeping their sum fixed at 16 equals 4 times big A. Let a prime sub 1 equals 4, and let a prime sub 2 equals 4 plus 2 minus 1 equals 5. Then a prime 1 plus a prime 2 equals 4 plus quantity 4 plus 2 minus 1 equals 4 minus 1 plus 4 plus 2 equals a1 plus a2. Hence, 4 plus 5 plus 2 plus 5 equals 3 plus 6 plus 2 plus 5 equals 4 times 4. Well, I guess I'm wondering about that. It says we next observe that a prime 1 times a prime 2 is greater than a1, a2. Clearly, this is true since a prime 1, a prime 2 equals big A times the quantity big A plus k minus h equals a squared plus k minus h times a. Since a1, a2 equals a minus h, a plus k equals a squared plus k minus h big A minus hk, from which it follows that a prime a1 plus a prime a2 equals a1, a2 plus h times k, where h times k is positive. By definition 1, this means that a prime 1 times a prime 2 is greater than a1, a2. Thus, a prime 1, a prime 2, a3 dot 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 an is greater than a1, a2 dot 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 a3 dot 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 an. If now big A equals a prime 1 equals a prime 2 equals a3 dot 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 an, there's nothing more to prove. If not, then there's at least one of the new set of n numbers, a prime 1, a prime 2, a prime 3 dot 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 an, which exceeds big A, the average, and at least one which is less than A. Call them B1 and B2, repeating the above argument with the rules of A1 and A2 taken by B1 and B2, we can find another set of n positive numbers with some n times big A, the average, whose product is larger than the product of the set, A prime 1, A prime 2, A3, da da da, A sub n. Well, that's kind of, I guess that's pretty interesting, and I kind of leave off for that for a moment. If we repeat this process over and over again, then after at most n minus 1 steps, including the first, we shall have constructed a set of n positive numbers, all equal to the average, with their sum equal to n times the average, and with their product larger than the product of any other n positive numbers with the same sum. It requires thought to see that at most n minus 1 steps are required. It's combinatorial enumeration, and it would so follow that the A1 and A2, after it results that are the most ones picked, that as it picks it down, it gets down to whether they're equal or that they're minimized in a sense. So then let's mark the little square box, which is another way to write QED, quod erat demonstrandum. So that's done. So what I'm thinking about that is the method that he's applying is about this, what would be when it's written out in longer forms, and the series and the infinite is these telescoping series, and these the scaffolding is what the concept has been here in terms of the telescoping series. And so the telescoping series is basically that in terms of something that's articulated or otherwise kind of folds out like a telescope, it slides out. And so the idea is that in the extension of this infinite series, then if you collect numbers in the pairwise or in groups as they go along in a layer of the scaffold or level of the scaffold, then is it fair to say that you have one infinite series that's kind of like the sum of the products 1 over 2 sub I, and another one that's kind of like 1 plus 1 over n or something like that adds up to or multiplies up to e. Now, is it fair to take 2 of one and 3 of the other and then call that a term and then cancel them? Or like to otherwise sum these two terms, to treat any 2 of the terms pairwise only by that power or the order of the place where they live in the telescoping and the scaffolding. And so it's not. It's more so possible that it can be possible to define pairs of sequences whose terms are so as determined in their contributions in order by something that results as a quantity together. Those can be pairwise, term for term, summed up, resulting a series that's a sum of series. And so, otherwise, though, I wish I would recall further on that, because it's one of the things that I find in terms of recurrence relations and the telescoping in series and the treatment of series and sums according to arithmetic, to add them together pairwise or in term-wise, or in the collection of groups of them, that it is it's one thing to say that term for term that 2 infinite series add up, then it needs to be made in a sort of way that the terms can't be rearranged, that rearranging terms in these series and then calling those addition is troublesome, because maybe it's as for this, because later something is going to come along and expect to use a numerical method to start crunching out the first contributions and get out the primary terms or the major contributors to the terms. And if there's been any exchange in the order of these terms that go up as summing up the formulas in the pairwise, then that would be bunk or bogus and otherwise contrived or possibly false, and if not erroneous, then invalidating the expectation of the error term and such. So that said, then about this idea of making these brackets about the numbers, taking the products of a group of numbers and figuring out that when they're equal, you can have the most numbers with the smallest product. then when they're regular in this way, when they're alike, when they're in the same category, say. And this kind of reflects on when we were talking about the systems of equalities and systems of inequalities, that the systems of equalities, as they don't have an index of the expression in their expression, it can be treated as a constant and multiplied out and fall out, kind of like equalities are the most number of expressions with an equality or an inequality together. They can be put into a list and have the briefest content, while inequalities, the more they are, the bigger the bounds between them, this can be so expressed, are farther apart. We almost start to look in ways to write the objects of arithmetic as the objects of inequalities as underneath their definitions. So what I'm talking about is yet another deconstructive account of the elementarily the objects of arithmetic and the objects of systems of equations. And the reflection on, for example, that that an object in the universe is everything that is not, or that the elements counted out from 0 are that much different, or whether or not they are that much less different than the other numbers, about how they fit in the middle. And then particularly in this context, how is that the unit circle or the unit square of centered on the origin, say, or with area 1 vis-a-vis the 2x2 box, or what, or the circle with radius pi, as it were, but these make for examples, and that's contrived, but it's a thing. These make for examples of then what falls inside those and what falls outside those. And then for these notions of the inequalities and some of these basic methods that are coming up to express for the arithmetic mean, that the arithmetic mean is being used to establish some of the properties to make for these expressions of otherwise when the equals part holds, the greater than the equal, then about when they don't, that it's possible to think of those variously in terms of numbers and their magnitudes. All these numbers so far are positive. And what that means in terms of how wide the box is. And so when there was the discussion briefly of something like the doubling space and this and that, and then also with the univalent, and what that means in terms of this being for non-standard character, and how that really lives and has real character in otherwise the infinite, and how that's real and reflects what is the necessary for these sorts of forays into discovering mathematics beyond the modern. That that's reaching quite a bit to get to where otherwise though the idea is to make it so that the properties of collections of numbers by their products or their sums, and then how those go into computing things like summary statistics, average, here the arithmetic mean or the average, is to be figuring out how many samples to keep to have enough memory to figure that you have a good guess of what the next estimate is going to be. For example, if they're all of a given size and the next one is within a certain range or bucket, then you can discard the oldest sample or otherwise fold it in. And how much that would change. So when we go from just like, here's a list of numbers and here's our average, to like, here's a list of numbers and I've got a new one and I must discard an old one. And that's my hand or what memory I can use to keep a summary statistic. And with those, I need to figure out what the best guess is of the next number to arise. And whether it's only possible, for example, when you pick a new one, to either discard it or discard the oldest one. Or you pick a new one and you can either discard it or discard the middle one or the most extreme one. How these things effectively relate things for what are that the sample mean is always different than the true mean formally until you've made all the samples and have a complete population. That inside, otherwise, the world of classical probabilities, the idea is to figure out what that means in terms of those alternatives and what can happen, and then what happens when there's basically various machines and randomly they do one of these things. What their view will be of the thing. Well, anyways, that's getting around the corner. But the idea is that there's lots to be worked into these elementary objects and the accounts of them and the reconstructive accounts, the constructive accounts, and here in the fact that arithmetic and geometry and algebra all come together around the same globe of these things is to figure out then what that means in terms of all the different ways they can come together and be a part and this kind of stuff. So, and so far as that goes, what you might figure is that I would try to figure out some more about the summary statistics. Because what would interest me most is to figure out what would be the most economical sampling units that keep the most information with the least, so that the best. I'm trying to figure out how to optimize these things given limited resources, given fixed resources, because there's no free lunch. Hey, have a great day.